In the previous episode, we learned how to create pods manually, but there's a big problem with standalone pods. If a pod crashes or disappears, the application can go down completely. And this is where deployments and replica sets become extremely important. A deployment allows Kubernetes to manage pods automatically. It can keep applications running, recreate failed pods, scale applications horizontally, and perform rolling updates with almost zero downtime. On the right side, we can see the architecture. The deployment defines the desired state, in this case 3 replicas. Then the replica set ensures that 3 pods are always running. So if one pod fails, Kubernetes automatically creates another one. This is one of the core ideas behind Kubernetes: self-healing and high availability. Now we can clearly see why deployments are so important in Kubernetes. On the left side, we have self-healing. The replica set constantly checks if the desired number of pods is running. So if one pod crashes or disappears, Kubernetes automatically creates a new one to replace it. This is one of the most powerful Kubernetes features because applications can recover automatically without manual intervention. And on the right side, we can see horizontal scaling. Instead of running a single pod, Kubernetes can create multiple replicas of the application. This improves availability, scalability, and traffic distribution across pods. So deployments are not just about creating containers, they're really about keeping applications alive, scalable, and resilient automatically. All right, now instead of writing the deployment manifest completely from scratch, let's do something much more realistic. In real DevOps environments, engineers constantly use the official Kubernetes documentation as reference. So let's go to the official Kubernetes docs and grab a deployment example directly from there. This is the official Kubernetes documentation. And here we already have a working deployment example provided by Kubernetes itself. As you can see, deployments are more complex than pods because now Kubernetes needs extra information: replicas, selectors, labels, and the pod template. For this demo, we're going to simplify the manifest a little bit. Notice that the official example also exposes a container port. We'll remove that part for now because networking and services deserve their own explanation, and we'll cover that properly in the next episode. All right, now let's apply the deployment manifest to the cluster. This command tells Kubernetes to read the deployment.yaml file and apply the configuration to the cluster. The apply command is one of the most important commands in Kubernetes because it uses the declarative approach. Here we can see the deployment running. Notice the ready column showing 3 out of 3 replicas available. And here we can see the replica set created automatically by the deployment. And this is the most important part. We only created 1 deployment manifest, but Kubernetes automatically created 3 pods based on the replica's value. Now let's test one of the most powerful Kubernetes features: self-healing. At first, we had 3 running pods managed by the deployment, then I manually deleted one of them. Normally, if we were working with a standalone pod, the application capacity would be reduced, and that pod would simply be gone. But watch what happened here. After deleting the pod, Kubernetes immediately noticed that the desired state was no longer satisfied. The deployment expected 3 replicas, but only 2 were running. So Kubernetes automatically created a brand new pod to replace the one we deleted. Notice the new pod name at the bottom and its age of just a few seconds. The other 2 pods have been running for several minutes, while this new one was created automatically by Kubernetes. This is self-healing in action. Nobody logged into a server, nobody restarted a container, nobody manually created a replacement pod. Kubernetes detected the problem and fixed it automatically. Self-healing is only part of the story. Another major advantage of deployments is scaling. Right now, we have 3 replicas running, but what happens if our application receives more traffic? Instead of manually creating more pods, we can simply tell Kubernetes how many replicas we want. Scaling also works in the opposite direction. If traffic decreases, Kubernetes can reduce the number of running pods. Now, Kubernetes is terminating the extra pods and keeping only 2 replicas running. Before we finish, there's one more important capability provided by deployments: rolling updates. Imagine your application is running with 3 pods and you need to deploy a new version. Instead of stopping all pods at the same time, Kubernetes replaces them gradually. First, it creates a new pod with the updated version. Once that pod is healthy and ready, Kubernetes removes one of the old pods. Then, it repeats the process until all pods are running the new version. This approach is called a rolling update. The major advantage is that users can continue accessing the application while the update is happening. In other words, Kubernetes can deploy new versions with little or no downtime. Today, we learned how deployments and replica sets provide self-healing, high availability, scaling, and rolling updates. These are some of the core features that make Kubernetes so powerful in production environments. In the next episode, we'll learn how applications communicate inside the cluster using Kubernetes services and networking. See you in the next one.